Okay, now I would like to actually also cover another aspect of braking systems, which is the energy consideration of the brake, and also I would like to cover actually an interesting topic in some brakes, which is called self-locking brake. Um, but before I go into that, I'm going to cover this energy portion of brakes, and this is not going to be included, guys, on the final exam. Again, this whole lecture basically is not going to be. You're not going to be responsible for that. So when you apply a brake, one of the main issue with braking is that basically the brake can fade, and the fading of the brake means, if you are going downhill, for example, for a long time applying your brake, you will notice that the brake will begin to become less efficient. And by that, basically, the coefficient of friction of the brake is actually reducing as a result of the increase in the temperature of the brake. So how do you analyze that? So the easiest way to actually look into that is simply by considering the energy. Let's say you're actually going downhill, you went by some elevation, you have basically absorbed a potential energy, assuming that your velocity is not increasing. You're going at the same constant velocity. So that energy is actually going to go into heat into the brake, and that energy, it could be as a result of the potential energy, or maybe you are going on a flat terrain where you're reducing your velocity from a final velocity to some initial velocity, which is a very high velocity, to a lower velocity, or to a full stop, right? And then you also have the rotating energy of the wheel, right, which is 1 over 2 j omega squared. So either the kinetic energy, or both, you could kinetic and potential, and then also adding the wheel energy. So all that energy is actually converted into creating heat on the brake, and the heat that is going to be getting into the brake is going to be equal to the energy that you have transmitted into the brake, or transferred into the brake. So that energy is going to be converted into this value, the heat energy, which is the mass of the brake, or the brake elements that you have, which basically have the disc, and then you have the pads, multiplied by the specific heat capacity, which is Cp times delta T, right? So the energy, the mass of the brake, the specific heat of the brake, and then you will actually solve for the increase in temperature, right? So this is, that equation basically will directly allow you to solve for the increase in the temperature of the brake. Now, if you want to look at the cooling of the brake, right? So the minute that you actually apply that energy here, basically it's exponential, but it's very fast, basically, that that energy is going to be definitely absorbed into your braking system, and now you have that increase in the temperature. Now, if you actually look at the decay of temperature, you actually are going to look at Newton's cooling law, right? And then Newton's cooling law, I'm pretty sure some of you know it from your thermodynamics course. Here, T infinity is your ambient temperature, right? Basically, the temperature, between your wheel and your fender, basically where that wheel is located. Or primarily, you can think of it as your environment temperature, essentially, right? As the wind coming over to cool down your brakes. So T1 is going to be your initial temperature, right? T infinity is your ambient temperature. HCR, or it is basically the convection coefficient of heat transfer. So that is your H, and then this is a property of the material, and it is also a property of the air that is being actually circulated around the brake. So it basically depends on the geometries and etc. And this is usually given to you, or you can basically calculate it by computational fluid analysis, or computational fluid dynamics, which is called basically CFD. A is the overall surface area of the brake, and then W is the mass of the brake, and then here basically you just pay attention to units. CP should be given in the same unit as pounds in this case, British units. So ultimately here, basically starting from an initial temperature. So let's say as a result of this equation, right, you had some potential energy converted to delta T. So you have that delta T, and you want to see how long it will actually take for the brake to come back to the ambient temperature. Right. So right now you are at T1. So you notice here that when T is equal to 0, right, this guy is going to be equal to 1, right? E to the power of this value, whatever, e to the power of 0 is going to be 1. So T minus T infinity is equal to T1 minus T infinity. So T is equal to T1. And when T is actually equal to infinity, then this guy would be 0, and then T is going to be equal to T infinity. So this is your traditional exponential decay function. And then this is how it looks like. So, you basically, you're going down, you apply the brake, your temperature suddenly increases, and then as you let go, basically you are going to cool it, right? And then let's say you push the brake again, instantly you're going to go up, very rapidly as a result of, transfer of energy over to your brake, right? The energy transfer is not going to take time. It will basically happen instantly in this case, or very quickly. And then when you cool down, when the brake cooled down, basically you're going to be following. Okay, so this is some of the energy consideration that would basically occur in brake systems. And by the way, fading, right, or in Arabic, basically, when they say, الفريم مثلا بلط, right, or it has no more capacity to basically to apply friction on large equipments, or maybe mainly like trucks. Basically, you are losing that brake. That is why you have to really don't apply the brake as much as possible to keep the temperature of the brake low, right? So by this, so you apply the brake and then you stop, right? And basically you give it more time to cool down before you apply a brake another time. All right, so the last thing that I would like to cover is basically self-locking brakes. And self-locking brakes essentially occur when you have, and what I would actually do here is I'm going to actually stop this, and I'm going to open a video where I can actually draw something for you guys and then explain that on paper. All right, so this is a self-locking brake, and I want to give you guys an example on that. So let's say you actually have a cart, and the cart is actually moving to the right with that velocity, right? And the way that I'm actually applying the brake on the car is basically I have like, an element that looks like that, like, a piece of metal that looks like that. And actually I have, this is my brake material, right? So this is one, and basically here you are applying the brake by applying a torque, right? So this is your torque, and then you're applying a torque on this guy and hoping that this guy would stop it. This guy is going to the right. And again, the same design basically. So this is my cart. But instead of actually having the brake on the front, I actually have the brake this time on the back. So this is my brake, which look like a handle, and I have a torque applied on here. And then again, this guy is going with that velocity. So which one do you think, where do you think I'm gonna have to apply more torque to basically stop the car, right? This one or this one? Maybe you should take some time right now, maybe pause the video and then think about it. And ultimately, you would actually see that this is a brake that is going to be the most efficient one. And by most efficient, basically, what I mean by that is I need to use less torque to be able to generate the same torque or to generate the same friction force, right? So the way you do this is basically we can do a free body diagram on here. And let's say this guy is my normal force, right, which is responding to my torque. The friction in this case is actually going to be opposing the direction, right? So this is the direction of the motion. And I know that this is my friction is going to be mu times n. And then we already discussed asperity contact, meaning this is your friction, right? Mu times n. In this case, you are going to the right, right? So the friction is going to be obviously like that. And then this is going to be your normal torque. So what I would like to do right now is I'm going to sum the torques about, 0.0 here, right? So if I sum the torque about 0.0 on the top figure, what do I get? So if I'm using my, clockwise directions, so I'm going to get T, right, minus mu n. So I need to know that distance. So I'm going to actually call that distance to be A, and I'm going to call that distance from here to be B, which are the moment arms of the friction and the moment arm of the normal force. So summing the torques in that direction, I'm going to have T, right? And the mu times n is actually helping the torque, right? So plus mu times n times A, right? And then the normal force is actually opposing the torque, so minus n times B. And then this is going to be equal to 0 because I have no inertial load. So the torque that I'm actually developing, I'm going to factor out my n. So it's going to be n B minus mu times A. Okay, so this is the torque required, right? Or the torque that I'm actually applying on this object as a function of the normal force, right? And in this case, right, if I actually do the torque, right, summing the torque about, let's actually call this 0.01, right, about 0.01. And again, I'm going to actually do it in that direction in this case. So I'm going to end up with what? So T, so the distance between N and this guy is B, and then that distance right there is actually A, right? So if I sum the torques about this point, I'm going to end up with what? So T, right, minus N times B, right? And then how about this guy, mu times N also, mu times N is actually negative, mu N times A is equal to 0. So the torque that I'm actually applying as a function of the normal force is going to be equal to N mu A plus B. So the main differences between these two torques are here I have N B minus mu A, and then here I have mu A plus B. So what actually happens is that, so you can already tell that you need actually less torque here to stop the car going in this direction than in this direction. And this is actually being reflected over here, right? Here the torque is less. Why? Because I have B minus mu times A, right? In this case, the torque is going to be more because you have both of these are positive. And in this case, actually, it may be actually possible. So let's start. So this is actually called a self-locking brake, right? Or self-energizing brake. And the reason why it's called a self-energizing brake is because the friction is actually helping the torque that you are applying. So you're applying this torque, and then the friction is actually helping you to apply this torque, and that is why you actually need less torque than that. But it is actually possible to actually make that brake self-locking, and the way that brake would become self-locking is when B minus mu A is actually less than 0. It means that your torque is actually less than 0. So you don't even need to apply torque to actually stop it. So all you need to do is to basically release it, right? And then this is a case that actually occurs in some of the door stops, right? So if the door is like this, right, the door is hinged over here and here, door is like kind of rotating like that, it actually has a self-locking brake, right? So some of the doors like that. So that door is actually opening like this, right? And then this guy is on the end. So this is called a self-locking brake. So it would be a self-locking brake by making B minus mu less than 0, or your coefficient of friction has to be greater than B over A, right? So you want to choose like rubber material, for example, where the coefficient of friction is greater than B over A. So I'm going to come back to my slide, and then that way I think this will make more sense to you right now. So this is your door stop, right? And if the door is going to the right, left, basically this is a self-locking brake, right? Why? Because the friction is actually now helping the torque. That here the torque is actually 0. Why? Because your coefficient of friction on here is made to be greater than B over A, where B in this case is a distance, is a vertical distance basically that we have over here, right? So that is your B. Okay, sorry about this because I can't really right here. So that is your B, you can see right here, right? And then this is your A. Okay, so some applications to that is in clutch systems, right? And then this is called a shoe type of brake, right? And here basically these are like, the pads, for example, right? That are basically, or the brake lining, right? So this is called, the laces or the brake lining basically are here. And if this guy actually, let's look into this guy. What if this guy is actually rotating in this direction? Right, the drum is on the outside here, and let me actually try and throw the drum. Maybe move it a little bit. Okay, so the drum, the red part basically is rotating, right? And then the inner diameter or the inner circle here is actually part of the drum. So if you are actually applying a brake over here, right, if this guy is rotating in this direction, opposite to the arrow that is shown here, you would actually see that the brake wouldn't be self-locking, right? But if you rotate in the opposite direction, right, if you actually rotate in the opposite direction, then the friction is going to be how? The friction is going to be opposing the direction. No, I'm sorry. So in the direction that is actually shown right now, right? Let us actually draw the friction right now. So as a result of, the red part rotating in the same direction as this arrow, right? How would the friction look like on the brake? The friction would actually look like that, right? Like this, right? On here, right? Okay, so as a result of this rotation, right? these, the brake on the inside is basically fixed, right? And on the outside is rotating. And now you can actually see that this friction is actually helping out the torque, right? So, this would be, for example, the moment arm of the friction. Right, so this guy right there is going to be the moment arm of the friction. And you see that the friction is actually helping the engagement force that you're applying. So this brake is actually locking in this direction. But if you actually reverse the direction of the drum of rotation, basically, in that case, basically the brake wouldn't be self-locking, and you actually need a lot more torque to actually apply, which is here, right? This is your energizing force in this case, right? So basically you're applying that force, or it could be like you're applying the torque about this pin and then that pin, right? So if you rotate in opposite direction, right, then the friction would be in opposite direction, and then the friction actually wouldn't be helping your engagement force. But if you actually make the brake in that configuration right here, so if you actually rotate in that direction, and let's do that, if you make this arrangement like that, basically if you rotate in that direction, then your friction over here is going to be in that direction, right? And right, it's basically right? So if you are rotating like that, basically you are pushing this guy in that direction, and that friction basically is going to be helping FA. But on this end, your friction is going to look like that, right, on this guy, and then that friction is basically opposing the moment of FA. So FA on here is like that, right? That friction is opposing the moment about FA about this point. So this arrangement, basically, it would allow you to create that self-energizing mechanism in both directions, and then this is useful in developing or in many brake systems. Okay, guys, so that is it regarding the material that I actually wanted to cover. I'm actually going to be posting one, very last lecture on gears, and again, gears are not going to be covered, and I will post a lecture and then a presentation that actually guys walks you through, how you find the efficiency of entry gear trains that you may need later on as part of other courses that you may be interested in taking on later on. Okay, guys, so that is it for this lecture.